Good morning, class. I hope I'm audible. And I see that people are still joining the lecture. So maybe I'll wait a few seconds before getting started with the topic for today. All right, we're going to get started. Um, and just to start things off, um, just a second. Yeah, just to start things off, um, a few quick announcements slash reminders. All of this information is going to be there on Canvas for you. This is just a reminder. Homework 2 is on Canvas. It's due next Thursday. That's October 1st. And in this homework, you'll be exploring ideas around linear models, the expressiveness of linear models, basically by building um, little linear classifiers for different kinds of functions. And then there is we'll be talking about mistake-bound learning. Today's lecture is all about mistake-bound learning, and we will be covering pretty much everything you need for that question. And on Thursday, we'll look at the perceptron algorithm, and the goal is by Thursday you'll have everything you need for the entire homework. That gives you still a week to do the whole thing, to do the perceptron, and hopefully after today you'll find that the mistake-bound learning question is good exercise to revisit today's lecture. There is some discussion on Canvas, and yes, I have been following it. I noticed that there was a lot of discussion on mistake-bound learning, so I decided to kind of keep those questions aside for until after today. But Anthony, did you have anything specific in mind? After lecture, okay. Maybe you'll ask the question after the lecture. Sure. The lecture schedule, as of course you probably are aware, is lagging a little bit behind what we had planned at the start of the semester, but I still think that there was enough room at the end, so things have moved around a bit. The thing that really suffered because of this and because of other reasons is the project first milestone, but I'm happy to tell you that that is done. Project details are posted on Canvas, so it should be available now. The task that you'll all be working on for the semester is to predict whether a certain trial led to a guilty or a not guilty decision. So the input here, the instance for this classification problem is the text of the trial. You don't have to worry about the text. I have featureized it for you. In fact, there are multiple feature sets that you can play with. And this will use the data from about 17th century to maybe 19th or early 20th century cases from this court called the Old Bailey. There's a document, a PDF on Canvas that gives you a lot more details about the task and the mechanics of how we will work through the project. Please go through that. This is going to be a big part of the learning experience in this class, because this is where, in some sense, you'll have unsupervised play, so to speak, where you get to do what you want with this data. I mean, within reason, subject to the rules that are in the document. There are many milestones associated with the project. The first milestone is a rather simple one, so you have a week for it. It really does not involve much. All you have to do is click a link on that is in the Canvas quiz. That will take you to Kaggle. If you already have an account on Kaggle, log in. If you don't, create an account, and you'll have to join the project. Once you join the project, you can download the dummy submission that we provide, that you can then upload to not Canvas, upload to Kaggle to see if it works. At the end, you need to come back to Canvas and tell us what your Kaggle username is so that we can find you, and what what Kaggle tells you when you upload the dummy submission. This is mostly so that you get comfortable with the mechanics of Kaggle. So this should not take more than 15 minutes. So please do it as soon as you can, and then that way you get to start playing with the project. Um, are there any questions about the project or the homework? What do you mean by start playing with the project? Basically, what we have is we have given you uh, a data set which has been featurized in 3 different ways. So essentially, you just have feature vectors plus extra attributes for each trial, like how old was the defendant, how many victims were there, and so on. Now, so essentially, you have multiple feature representations for the same sets of inputs. The goal of the project is for you to be training multiple classifiers, at least 6 classifiers, running their predictions and building them locally using the test and the train and the test set that we provide, and uh, then you change the uh, test set to another set that we've given you, evaluation set, where all the labels are hidden. You make the predictions for that evaluation set and upload it to Canvas. What Canvas will do is it has its own evaluation. It will evaluate all these submissions that you provide and then put you on a leaderboard. And so the goal of the project is that you play with at least you implement at least 5 algorithms. Did I say Canvas? I meant Kaggle. Yes, Kaggle will do all the entire project is on Kaggle. Canvas is only for submission. So you'll have to upload at least 6 different submissions to Kaggle. At least 6. In the past, when I've done this, some people have done like dozens of them, and some people have done 6. It's fine. So 6 is the minimum. Um, and you do 6. You upload 6 runs, the results of 6 runs. What will happen as a result is you will be placed on the leaderboard. And so you can have, for example, a run called, say, decision trees, um, using these features with this depth limit, and that'll get a certain accuracy. You may have a different run, say SVM with some feature transformations, and that'll get you a different accuracy on Kaggle. So out of the 6 runs, I insist that at least 5 of them should be your own classifier implementations. What that means is whatever you do in the homework, you can very quickly turn it around and use it on the project also. The 6th one, you're free to use any learning library you want if you choose. Otherwise, the 6th one can also be your own implementation. Um, there has been an even split of people who want to explore a learning ML library on their own, or use their own implementations. We will cover more than 6 learning algorithms, so that shouldn't be a problem. So the rules of the project are the following. There are at least 3 feature sets, if not more, because if you include the extra attributes that I give you, there's probably 4. What you need to do is explore at least 2 different feature sets. So what you could do is the same algorithm, you could run it on 2 different feature sets, and that gives you 2 runs. So explore at least 2 different feature sets. You need to explore 5 algorithms, 5 different settings. So this could be, perceptron, SVM, logistic regression, decision trees, committees of trees, and so on. And one of the 6 submissions can be code that you did not write. So it could be a machine learning library. If time permits, sometime towards the end of the semester, we'll do a tutorial on one or more of the ML libraries, or you can talk to us in office hours. Does that clarify what I mean by playing with the project? There's also another thing you could do. You could try to invent your own features. So I'm not going to tell you what accuracy I got with the features that we have, but there's a good chance, there's more than an even chance that by inventing your own features, you will be able to outperform simply simply the training a classifier on the features that I have provided. How do you invent your own features? You can combine existing features. You can look at the extra attributes that I have provided and create some extra dimensions, or you could apply feature transformations. All of these count. Any other questions? So there's a PDF that lists out a lot of these things on Canvas when you go to the quiz, and we'll clarify things as we go along. As I think about it now, there's at least one inconsistency in the PDF that I'll fix right after the class. But in general, you are generally free to pick which algorithms you want. You don't like decision trees, don't use it. You don't want to use perceptron, do something else. It's totally fine, as long as you stick to the ground rules. Any other questions? Off topic. So right, so this is the other set of questions. So it's not off topic. The question is for homework 2. Do we need to show how we arrived at the linearly separable or not linearly separable decision? So the question, if I remember right, does not ask you to. So sadly, I have to say you don't have to. But if left to me, I would like you to justify. The homework, the general instructions for the homework does actually say your answers need justification. So what I would recommend is the following: if you have if you decide that a function is linearly separable, show a linear classifier that is the function. You don't have to prove that it's equivalent. You just need to show that it's the same function, and we can check. And if it is, you're right. If it's not, you're not. And if it's not linearly separable, you can write maybe a one-sentence description of why. You don't need to spend too much time on the not linearly separable case, because that could be a little bit trickier. So if it is linearly separable, show a classifier. If not, write up to one sentence that says why you think it's not. Does that answer your question, Jacob? Any other questions about the project or the homework? I also found out that over the weekend there were issues with the lecture slides. I hope it's all fixed now. When I checked, it works now, but send me a message on Canvas if the website's down and you can't access the lecture slides. I'll try to get things to Canvas if necessary. All right. Are there any other questions? If not, like I said, you have the entire semester to be playing with this. This is kind of it has the potential to be a fun project. There are many interesting things you can also explore here, because essentially these are decisions that were made by judges about people. There are questions of fairness and ethics that we can think about. At the end of the semester, you will be writing a report for the project where you describe what you did. And I want you to think about these things also when you're thinking about the project. All right. So if there's no other questions, I'm going to start with so there's a question. Can I explain what a linear threshold unit is? So what I meant when I said a linear threshold unit is equivalent to. So let me explain with an example, because that might be the easiest thing. So let's say we have some function. I'm going to use an example from the lecture, because I have forgotten what Boolean functions were used in the homework. So let's say we have x1 and x2 and x3. And the question is this linearly separable or not? So how do you check for this? There are a few different ways of thinking about this, but let me first tell you the answer and then tell you how I got there. Now, this function is it's a it's a function that takes three variables, x1, x2, and x3, and tells you true or false. I claim that it's exactly identical to x1 plus x2 plus x3 greater than or equal to 3. This is I claim these two things are equivalent. So let me so these two functions are equivalent. What do I mean by that? That means whenever the top function says true, the bottom thing will also say true. There's an easy way to check for this. What is the meaning of uh, this Boolean function? The Boolean function says the output is true when all of them are true. Remember that true equals we represent true as 1 and false is 0. So when you look at these three things, the output is true when all of them are true. How many of them are there? So there are three of them. So the output is true when the three of them, each of them takes the value 1, which means only when all of them take the value 1, the output is the Boolean function returns true. But when all of them take the value 1, their sum is 3. So there's only one way in which the sum can be more than 3, and so this function is linearly separable. Now, you may think that seems like somewhat of a bogus argument. So here's another way of thinking about it. Or rather, I didn't tell you how I came up with it. I just told you what the answer is. The way you come up with it is you think of m of n functions. This is one way of thinking about it. When you think of m of n functions, you identify which variables are relevant. So here we have three variables that are relevant, x1, x2, and x3. And you want 3 of x1, x2, and x3 to be true. So you add up all the things that are here and you say 3 of them should be true. What if you have a negation, not x? When you have a negation, what you do is let's say instead of x3 you have not x3, which means this is no longer correct. So let me erase that. So this is equivalent to 3 of, again, x1, x2, and 1 minus x3 are true. Not x3 is just the same as 1 minus x3. There's a discussion on what is and or. Let me just give you a good way to remember this. The upside down thing looks like an A, so it's an and. So the three of these things are true. So we have the sum of these three things should be more than 3. So x1 plus x2 plus 1 minus x3 is greater than or equal to 3. Now, what about an or? When you have an or, instead of and, let's say you have an or. So you have or here and or here. But or is also the same as at least one of these things is true. So you just have 1. And you can keep playing with this. So this is just one way of thinking about this. And I want you to, another way of thinking about this is if you have only two variables, you try to plot them on the two-dimensional plane and see if you can draw a line between them and so on. Basically, this question, the warm-up question, is meant to kind of make you think about what linear separability is and force you to explore with small examples what can and cannot be linearly separable. The formal way of proving that is a little bit more tricky, and I'm not going to talk about that, but those of you who want to think about this, it involves one way of formally checking whether something is linearly separable might involve setting up, say, a linear program and checking if it's feasible. Those of you who understand what I said might want to think about how to do that. And those of you who didn't, don't worry about it. All right. So let's see if there's another question. There was a question before that I missed. There's a button, take the quiz at the end of project instructions. Do I click on that for the submission, there's no submission yet. Basically, it's just a quiz. You just need to give us, so click the link on Canvas, go to Kaggle, register, and do all that. And then make a dummy submission, come back to Canvas, and then tell us your Kaggle ID and what Kaggle tells you when you upload the dummy submission. And at that point, you'll have to take the quiz. I don't think there are any limits on how many times you can take the quiz. If there are, I will fix it. Let me know. The final answer for going back to this linear separability thing, my TA just reminded me. So I would, just so that we make it easy for grading, I would like you to simplify this into something like a weight vector and a bias. So you may have something greater than or equal to 2. And so this corresponds to the weights of for x1, x2, and x3, it is 1, 1, and -1. And the bias, so let's put it this way, -2 greater than or equal to 0. So the bias is -2. So if you write it like this, it might help us with the grading, because we'll just be looking for this and move on. And if you basically if you simplify the thing and write it in just as a collection of weights and bias, it'll help grading. All right. So are there any other questions? I feel like we've spent more time on this these 10 points in the homework than maybe the 10 points are worth. But if you feel like this is helpful, that's good. I'm going to move on to the lecture. And of course, if there are more questions, please come to office hours. I'm going to move on to the lecture. Today's lecture is about online learning, or actually a small subset of online learning, which we'll cover in the class, called mistake-bound learning. So just to kind of tell you where we are in the context of the rest of the class, in terms of the big picture. Earlier, we looked at linear models. Not exactly last lecture, but maybe 2 lectures ago, we looked at linear models. And in the last lecture, we had this discussion about what does it mean for a learning algorithm to be good. There are multiple ways of answering this question. The question at the bottom, there are many different ways of answering this question. One way of answering this question involves online learning. And like I said, mistake-bound learning is a small subset of that. If you take the idea of online learning and combine it with linear models, we get named algorithms like perceptron, which we will cover in the next lecture, and another algorithm called Winnow, which sadly we won't have time to cover, and its descendants, which involve multiplicative updates. But we can answer this question in other ways also. If we answer the question using the framework of empirical risk minimization, or the PAC framework, and combine that with linear models, historically at least, it naturally led to the development of support vector machines. There are more ways of answering the same question. You can be Bayesian about it, and you might get logistic regression or naive Bayes, and so on. So if you think about it, there is really a combination of 2 things going on here. There is this question of how good is a learning algorithm, and we need to formally answer that. And then there is a model definition. By combining these 2 things, we get learning algorithms. So today, we are only going to follow one of these paths, and we'll keep revisiting this question multiple times, and every time we answer this question, we'll just get a whole bunch of new learning algorithms, many of which you may have heard of, like support vector machines or logistic regression, and so on. So this is our first foray into, in some sense, slightly more theoretical approaches to machine learning. So the plan for today is, first we will look at this model for learning called the mistake-bound model. This is when I say model, this is a model for analyzing learning. It's a formalized setting in which we define, this is what I mean, this is the protocol that the learner and the teacher will follow. And under this protocol, we will study how good whether learning can happen. And we'll encounter a definition for something called the a mistake bound algorithm. Then, just to convince you that the definition I'm showing you is not a vacuous one, there's at least one mistake bound algorithm that exists, I'll show you a proof of concept mistake bound algorithm called the halving algorithm. And then we'll apply the theoretical bound that comes out of the halving algorithm on some concrete examples. And then the plan is to wrap up this unit with some discussion about um, the connections between ease of learning and how you represent classifiers. The hope is we'll finish all of this within an hour. Let's see how it goes. So let's start off with the mistake bound model. Um, so the main lesson from last week's lecture is that in order to think about learning formally, we need to think about how the learner and the teacher interact with each other, what the protocol of learning is. And the main point from the last week's lecture was, last Thursday's lecture is, if you change the protocol for learning, you will get very different kinds of success. With teaching, the number of interactions with the teacher can be very limited. With active learning, it's a little more. In general, it can be a lot more. Here, we are in the context of mistake-driven learning, we are going to consider a very specific protocol that where the learner and the teacher interact. So the learner maintains at all points of time its current hypothesis of the true function. And learning proceeds in rounds. What happens in each round is, first, the learner gets an example. This example does not have a label. It's just an example. And then the learner makes a prediction using its current hypothesis. So that is HT of X. So the learner sees an example and says, this example is positive. After it makes the prediction, it then receives the true label for the example. And then if at this point it has the prediction and the ground truth, and if the prediction is not correct, then it makes an internal update of its hypothesis to come up with a new hypothesis, HT plus 1. At this point, the learner discards the existing example and then waits for the next example to come in. This is a rather simple setting. So the learner sees an example, makes a prediction, then gets the feedback and makes a potentially an update. All you need for this framework to work, for this protocol to work, is you need to define how to make a prediction using a current hypothesis and how to update the current hypothesis to a new one. So there's a clarification question: is HT equivalent to a weight vector? It could be a weight vector. In fact, when we come to the perceptron algorithm, it will be a weight vector. But here I'm talking about an abstract function. It's just some function. In fact, when we talk about the halving algorithm, it will be a slightly more involved function. HT is just some function. HT is some function that maps the instance space to the label space. In fact, all HTs are functions of that kind. So the question now to think about is, given that this is such a simple scheme, the model does not have, the learner does not have any memory to store a history of examples. The learner does not iterate over the examples again and again. All it does is makes a prediction and possibly makes an update. So the first question to think about it, can learning possibly work in this framework? But once you start thinking about that, we need to, you might realize that it's worth thinking about what does working mean. And that's what we're going to first formalize. This is the mistake bound formalization of what learning is. Let's get into a slightly more formal definition. We have an instance space, X, and it's an n-dimensional space. So there are n features here. And the goal is to learn a target function f that can map instances to labels. And we are considering binary classification. The labels are true or false, 0 or 1. We believe, for some reason, that this f is in some set of functions called C. C is the concept class. We'll call C the concept class. The size of C might be parameterized by by n, the dimensionality. We'll see some concrete examples of this for the purposes of if you want to imagine what this is. Imagine that C is say decision trees of depth no more than 5, for example. So the nature, we believe, for some reason, is allowed to pick its function only from within C. For now, we'll assume that C is also known to the learner. So nature, we have the true hypothesis space. The learning protocol, we just saw that, looks like this. The learner is given an example, X, and the learner doesn't get to control which example comes to it. It's possible that there's an adversary that wants the learner to fail, that only selects the most difficult examples at each point and presents it to the learner. We don't get to control that. And then the learner predicts a label, h of x. Once it predicts the label, it's given the ground truth, f of x. F of x is the true label. This is the feedback part of the learning protocol. Now, how do we define success? For the purposes of this framework, we are going to look at mistakes. We declare that for this particular round, the learner has failed. The learner has made a mistake if its prediction was not did not match the label that it then receives. So the learner has failed in this round if it makes a mistake. So this is just all I have described here is given names to things. Now, one of the things that some of you might be thinking is this is a lot of notation. And I just want to convince you that this notation is going to help us. But before that, I also want you not to get intimidated by all the weird symbols on the screen. These are just names for things. I mean, instead of saying every time the learner makes a prediction, I can say h of x. Instead of saying that the learner makes a mistake, I can say f of x not equal to h of x. This is just a formalization. In a similar vein, we are now going to formalize one more thing, two more things actually. Let's say the learner gets to see a sequence of examples. So it gets to see a sequence x1, x2, xn. Oh, not n, but let's say xm, some number of examples. It gets to see the sequence in this order. And the learner that we have is some algorithm that we are going to call A. And the target function is f. So we can ask on this particular sequence, when the target function is f, how many mistakes does the algorithm make on this particular sequence? So we can, so for a sequence S, number of mistakes on S by A if f equals target. This is this is just, you can think of it as just counting how many times this mistake happened. Maybe a mistake happened on this example, and maybe this example, and everywhere else it was right. So the number of mistakes is 2. This we're going to call MA of FS. So the number of mistakes made by this algorithm if the oracle function or the target function is f on this specific sequence of examples. Now, the thing for you to think about is, what are the things that we don't know or don't control here in this MA of FS? We get to control what the learning algorithm is because we are going to design a learning algorithm. We get to control that. But we don't get to control nature. So we don't get to control what the true function is. We have no idea what f is. And remember, we also don't get to control what the sequence of examples is. The sequence of examples can be anything. So then this definition is in some sense for one path for one function. So that's not something we care about. Instead, what we would care about is the worst case. Pretend that there is an adversary. This adversary knows the true function, and it knows all the instance space completely, and it knows your algorithm. What it does then is it constructs the perfect sequence that is going to make your algorithm fail as many times as possible. And what do I mean by fail? Make a mistake. So the adversary constructs a sequence of examples that induce failure for your learning algorithm as many times as possible. And this is the maximum among all. This is not even correct. So this is not f in S. This is f comma s. So among all functions, among all sequences of examples, the maximum number of mistakes made on that sequence for that function is a property of only two things. It's a property of your learning algorithm and the concept class. And that's what we're going to define. MA of C is the maximum possible number of mistakes made by this algorithm on any target function for any sequence of examples. Before I move on, let me let me see if there are questions, and feel free to type any questions. So there's one question: do we update HT for all examples in S? No. Remember, the protocol we are looking at is HT gets updated only if there's a mistake. So it does not get updated for all examples. In fact, you can think of HT as getting updated only when there is a mistake. So the number of updates equals the number of mistakes. There's another question: what is the oracle? Yes, so I do use the word oracle interchangeably with the target function. So oracle function equals target function. There's another question: I wrote the number of mistakes divided by S. Is this the ratio? No, there is no ratio. I said the number of mistakes on this sequence. It's not a ratio. It's the actual count of mistakes. Any other questions? What exactly does it mean to have a concept class parameterized by n? That's a very good question. And this is a question that we will have to think about a little bit more carefully. So imagine that you have 5 features. We can now ask how many, say, conjunctions are there with 5 features. Let's say the concept class is conjunctions, which is basically functions where we have and so on. So x1 and x7, x14, x14. So we can ask how many conjunctions are there with, if you have 50 features or if you have 5 features. The number of conjunctions there are is smaller, clearly, if you have fewer features. So the number of the dimensionality that you have determines how many functions there are in a very coarse sense. I mean, of course, that's an upper bound. If I know that the function class is a certain specific subset, then the number of features you have, the number of functions you have in the concept class is a function of depends on the dimensionality. This is what I mean. So the number of the size C is the concept class. It's a search space for the learning algorithm. It's the function. It's a set from which nature gets to choose its functions from. If you believe that nature is going to choose its functions from conjunctions, and if we are going to make the learner's job easy, we are going to tell the learner this is where nature is searching. So the learner is going to search this space. So I claim that the concept class is parameterized. The size of the concept class depends on the dimensionality. And we'll see this more concretely when we look at examples. For now, I want you to think about, say, the size of a truth table. Oh, sorry, the number of functions there can be. If you have only 2 features, there are fewer functions than, say, if you have 20 features. There's another question. If MA of C is the maximum number of mistakes for any sequence, wouldn't it just keep increasing indefinitely with a larger S? Do we just assume it slows down asymptotically so that for sufficiently large S, the error stops increasing? Now, this is a very interesting question. So let's think about this a little bit more. So the question is, this definition, MA, is the maximum number of mistakes that we can make. Why should this even be bounded? Maybe there is no algorithm that for no concept class will ever stop making mistakes. You can keep making mistakes. And the answer is not quite. And this is, I will prove to you right after this section that there's at least one algorithm out there, the halving algorithm, which actually stops making mistakes after a certain point. The Halving algorithm has problems. We can't implement it. It's an unimplementable algorithm. It's just this proof of concept. But there are other algorithms which have this really intriguing property. One of them, a famous one, is the perceptron algorithm. The perceptron algorithm comes with a guarantee that says, in certain situations, it will, after making a certain number of mistakes, it will never make any more number of mistakes, no matter how many examples you throw at it. And this is a formal statement that we will prove in detail. In this setting, yes, X is a discrete space. For now, we are only considering uh, discrete things. So, though technically for this particular definition, we don't, nothing on this slide requires X to be discrete. As far as the definition of mistake bound is concerned, X can be a continuous space. In fact, the perceptron algorithm, as I said, is a mistake bound algorithm, which operates on continuous features and searches through the space of weight vectors. So X need not be a discrete space, but in the example that I gave here, X was a discrete space. And X and C are finite. So far, not necessarily. Neither X nor C are defined to be finite here. They don't have to be. And because the only thing that we are counting is mistakes. We are not counting anything else. So neither X nor C have to be finite. For today's class, I will be only considering at finite sets. In Thursday's class, we will relax that and move to real valued features and real valued hypotheses. Other questions? Let me kind of take this forward a little bit more. I'm going to define an algorithm A. I'm going to call or name an algorithm as a mistake bound algorithm if this quantity, the number of mistakes, the worst case number of mistakes it makes for any sequence, for any function in the concept class, if this worst case number of mistakes is only a polynomial in the dimensionality. It's not exponential or worse. So if the number of mistakes it makes is not just finite, but actually a polynomial in the dimensionality, then we are going to call this algorithm a mistake bound algorithm. Let me expand on this a bit more. So this is my definition of learnability under the mistake bound model for learning. An algorithm A is a mistake bound algorithm for some concept class C if the number of mistakes it makes in the worst case is polynomial in the dimensionality. What that means is, given a concept class C, let's say an adversary chooses a sequence S of examples. And the adversary says, oh, actually, before it chooses a sequence of examples, the adversary chooses a function F. The adversary picks a function inside the concept class that it believes is going to be the hardest thing to learn inside this set. And now for this really difficult function, it's going to choose the hardest sequence of examples that are going to confuse the learner every single time, or as many times as possible. Then we can say that the number of mistakes that the learning algorithm makes, if the number of mistakes the learning algorithm makes on F and S is polynomial in N, if even though the adversary has chosen a function, and even though it has chosen the sequence of examples that are going to confuse the learner as much as possible, despite this, if the learning algorithm makes only a polynomial number of mistakes in the dimensionality, then and only then are we going to call this algorithm a mistake bound algorithm. Now notice that this definition is actually harder or more more stringent than the question that Adam had asked. The question that Adam asked is, why should that mistake bound ever be even finite? Polynomial is much more strict than finite. You can have exponential that is still finite, but I'm asking for something more strong. We haven't decided whether such algorithms exist. All I'm saying is, if an algorithm satisfies this property, we will bless it with the name a mistake of mistake-bound algorithm. Now, let's say, so for a certain, so this definition is for a pair, an algorithm and a concept class. Let's say there is a certain concept class for which there exists some algorithm. We may not even know what that algorithm is. We may be able to prove that there exists some algorithm that makes a polynomial mistakes, a number of mistakes in the worst case. If we can prove the existence of such an algorithm, then we are going to say that the concept class C is learnable in the mistake-bound model. So let's maybe look at these two definitions here. There are three definitions that I have made here so far. In the previous slide, I said this MA of C is the maximum number of mistakes that the learner makes for any sequence of inputs for any function in a concept class. So this is a property of an algorithm, a concept class, and an algorithm and a concept class. Now, this quantity, if this number of mistakes, worst case number of mistakes it makes, is polynomial in the dimensionality of the problem, number of features you have, then we call the algorithm a mistake-bound algorithm for this particular concept class. This is a property of an algorithm and a concept class. Then we can ask, is a concept class learnable? We can ask, for example, are XOR functions learnable? In order to do that, to show that under this definition of learnable, we are going to declare that a set of functions, a concept class, is learnable in the mistake-bound model if there's some algorithm that can actually learn it with a polynomial number of mistakes. Before we move on, are there any questions? How do you determine if this is a polynomial? I have shown you nothing practical so far. So I have shown you nothing that you can actually prove. So this is just a definition. We will see how we determine whether it's polynomial or not in the examples that we encounter. I will pass that on for future, for literally the next thing, and move on to the next question, which is why polynomial, why not some other function? And this is really an order of magnitude thing. Polynomials are smaller than exponential. Linear is the smallest polynomial. Sublinear, logarithmic, is smaller than linear, and so on. We are talking about just an order of magnitude. And this is like a standard thing across most of computer science, where we declare success as essentially, if something can be done in a polynomial time, then it's fast. If something, or rather, if it's the other way around, if something cannot be done in a polynomial time, it's slow. If something cannot be done with polynomial space, it requires too much space, because exponential, the difference is really exponential versus polynomial. If something can be done in sublinear time, then it is really fast. And this is really the very coarse cut that we are thinking of. And by polynomial, I mean, remember, polynomial includes everything, a polynomial of all degrees. So it could be a polynomial. So n, the dimensionality power 1,000,000, is still a polynomial. It's a ridiculously large polynomial, but it's still a polynomial. And this is the very, very loose definition of learnability that we have given for ourselves. And what we will show is even this loose definition allows us to show that some functions are not learnable. Some functions require an exponential number of mistakes to be made, which is too much. Exponential stuff grows too fast. Polynomial stuff grows less fast. That's just the intuition. I have to point out that this is not the most general setting for online learning. The number of mistakes is not even the most general metric for measuring success. If you are interested in learning more about this, look up the word regret. Or, well, if you look up the word regret, you're going to get all sorts of stuff. Look up the word regret in the context of online learning or regret-bound learning. And I can point you to resources that actually go into a lot more math about bounding regret, which is in hindsight we measure how far the algorithm would have been had it been given all the data at once. So there are a few things to keep in mind. I will connect this to streaming algorithms in a minute. In online learning, notice that we are making no assumptions about the probability distribution of examples. In fact, we are assuming that the examples are coming to you in the worst in a worst case setting. There's like an adversary that is generating the examples. All we are doing is following this protocol. For each example, the learner gets an example, it makes a prediction, and then the true label is revealed. All we do is just count the number of mistakes and nothing else. It's an extremely simple and intuitive model. It's actually fairly widely applicable despite its simplicity, because there are some cases where we may not have the luxury of storing things. Maybe you want an algorithm to be running inside one of these small devices that does not have memory, or maybe for other reasons you cannot store examples. All you can store is a model. So this has connections, as Ryan points out in the chat. It has at least intellectual connections to streaming algorithms, though we won't actually see any streaming algorithms in class, like Mr. agrees and other things. Instead, we will be looking at us. I mean, since you've seen these algorithms, it seems like I want you to think about the connections offline. The evaluation, as far as we are concerned, is we will try to make the smallest number of mistakes in the long run. And it's worth thinking about how this connects to the real goal of learning, which is generalization. I'm not going to answer that question now. We'll come back to that later on. There's a comment: is there noise in the data? And if so, how is it that the learner stops making mistakes? Effectively, what I'm going to argue is that even if we are going to assume that maybe there is, even if there is noise, it is controlled in a certain way. Even if there is noise in the data, the oracle does not get to pick its function from such a complicated space where the noise can be arbitrary. So in the theoretical setting, of course, we can be fed an infinite sequence of examples, and I'll comment on that in a minute. This is a rather simple model. There's no notion of data distribution. It's a worst case model. There's really no need for much memory. All you need is enough memory to store the hypothesis. It's, of course, not perfect. It has problems. The biggest problem is its simplicity itself. Maybe we care about not just the number of mistakes, but when the mistakes are going to happen. Maybe I don't mind my self-driving car making a mistake in wide open spaces, but I really care about whether it makes a mistake when I'm driving through a school zone. So, but as far as mistake-bound learning, these two situations are the same. So this is a rather simple model. However, despite its simplicity, the advantage is that we can already see many of the learning-related technical issues, even in this setting. And then there's a line of work called online to batch conversion, where there are generic conversion techniques from mistake bound to other ways to define success in learning. A question to think about is counting mistakes just enough? Under the mistake bound model, all we need is to bound the number of mistakes. We care only about not making mistakes. But there is a rather simple setting where the learner might see an infinite number of examples without making any mistakes, and it might seem like it's success. This is the case where the learner is given the same example over and over again, and it just remembers that example after one mistake. Under the mistake-bound model, if this is the case, it's okay. If the sequence of examples is literally the same example again and again ad infinitum, and this is the adversarial sequence, under the mistake-bound model, this learner is successful. We may not be able to learn a true function. We may not be able to discover generalization. We may not be able to do well on any other example. But since we have already defined the mistake bound model as counting the number of mistakes, this learner is not going to make any mistakes. And under the mistake bound model, it's successful. The question for you to think about offline is this sane? Is this a meaningful thing to do? Or maybe there's a problem with the definition. All I have shown so far is just a definition. And this is important. I have given you a definition of a set of concept classes and said this concept class is learnable, and this concept class is learnable if it has this property. There is no reason for this set to have even one set of functions. Maybe I have just defined a set that does not contain anything. Maybe no concept class can be learned under such a stringent rule where you're allowed only a polynomial number of mistakes. To prove that that's not the case, I'm going to now introduce a proof of concept mistake bound algorithm called the halving algorithm. So the question is, can mistake bound algorithms exist? And the answer is yes. If you don't care about memory at all, the halving algorithm is a mistake bound algorithm, and we'll prove that. Let me show you two generic mistake bound algorithms actually. The first one is called, we'll see that in a minute. One of them is called consistent, or in short, we'll call it con, and the other one is halving. Both of these are conceptual things. You won't be implementing them. These are just proof of concept things that show that something exists. Let's say, for the purposes of this argument, let's say C is a finite concept class. The goal is to learn some function inside the set. I'm going to define this algorithm con. Con is short for consistent. That does the following thing. At any stage, it maintains a set of functions in its memory. We're going to call the set of functions Ci. Ci in stage I is a set of all functions inside C that are consistent with every single example that was previously seen. So if say you have C is a set, the concept class C is a set F0, F1, F2, and F3. And let's say, maybe, let's say F0 disagrees with example 1, and F3 example 2. If F3 disagrees with example 2, then after 2 steps, C2 would be the set F1 and F2. It keeps only those functions that agree with the label for every example that was previously seen. So this is the update step. If it makes a mistake, it will remove all functions that disagree with that thing. Next, we need to say how a prediction happens. At prediction time, what this algorithm does is it has this set Ci, right? So we had Ci is F1 and F2. It picks a function randomly from this set and makes a prediction. Remember, for a mistake-driven algorithm, we need to only define two things. We need to define how a prediction is made, and we need to define how updates are made. The updates is essentially pruning the set that we have to only keep those functions that are consistent with the current example and all the examples so far. The prediction involves picking a function randomly, maybe F1, and saying, and the output of this learner is the label of whatever F1 gives. The first thing to note, and this is it, this is the entire algorithm. The first thing to note is every time a mistake is made or not, it doesn't matter, Ci plus 1 after seeing the ith example is either equal to Ci or it's a subset of Ci. When can it be equal to Ci? If no mistake was made, then it removes no function. So the function Ci plus 1 equals Ci. But if a mistake was made, at least one function, the function that was chosen, made a mistake, because that was what was used to make a prediction. At least one function makes a mistake, so it gets thrown out. And maybe all the functions that make a mistake gets thrown out. So either Ci decreases in size or it stays the same. So ci plus 1 is a subset of ci at each step. But what this means is if a mistake is made, then ci plus 1 is going to be strictly less than a subset of ci, because at least that one function that made the mistake got thrown out. So the size of ci plus 1 is strictly less than the size of ci, which means progress is made. Why is progress made? Because we have a finite concept class. You can't keep reducing this because we know that there's at least one function that is consistent with every example that can be thrown at it. So all you have to do is basically keep removing things till we are left with a concept class with we are left with some ci that has exactly one example, which means the maximum number of mistakes this could possibly make is the size of c minus 1. So at least it's finite. I mean, yes, of course, we had only a finite number of functions to deal with. So the best analogy for this is something like linear search. We have a search, we are trying to find a single point inside an array, and we keep going through it, iterating each step and seeing if it's there. And linear search, the complexity of it is we need to, in the worst case, look at every single element. So let me pause for questions. I see there are a couple of them. How does this algorithm deal with noise in the data? As far as this particular set of examples are concerned, we are going to assume there's no noise in the data. There is a single function f that's inside the concept class. So there's no noise in the data. It's just it's perfect. This is mostly a conceptual thing. We're going to it's a proof of concept. There's another question. Why don't we run some example on every function in the set and remove all functions that make a mistake? That's actually what, oh, I see. So we can do that. That's a different algorithm. I'm just giving you the name of you can create a new algorithm, and that's what it does. In this case, we are going to choose one function to make a prediction. We will, of course, remove all functions that make mistake. In case this representative f makes a mistake, then all functions would make a mistake. Otherwise, we will just pretend that nothing bad happened. This is the name of this algorithm. You can use another one if you want. I mentioned that we will keep removing exam functions from the concept class until we arrive at what? That's the question. So remember that the concept class is finite. We cannot keep removing functions, which means that there's only a finite number of things to remove. And we also know there's at least one function in this set, f, that is the true function, which means that it is always going to be correct. Which means in the worst case, we might remove everything but f, which means in the worst case, we might remove everything. We will stop when there is exactly one function in the set. In the set, the stopping criterion is stop when the size of ci equals 1. At that point, we know we found the true function. And at that point, we would have made how many mistakes? We started off with size of c mistakes. That's how we initialized the thing. And we removed everything except 1. So the number of mistakes is size of c minus 1. This conceptual algorithm is kind of ridiculous because it requires, oh no, so it is ridiculous because it requires a memory of all possible functions, but it does not require memory of all possible examples that have been seen because you can keep removing them online. You can remove, remember, this is you're not allowed to remember examples. All you can do is remember, instead we are remembering functions. You start off with this set, and then you see example number 1. Once you see example number 1, you create C1, which is a set F1, F2, and F3. And you throw out example 1. We're done. And then we see example number 2, it makes a mistake. So we create C2 is just F1 and F2. And we throw out the example number 2, and then we keep going. So at each point, we keep pruning the set of functions and throwing out the examples, but we don't need to remember the all previously seen examples. So the question now to think about is this a mistake bound algorithm? I've said that the number of mistakes is size of C minus 1. Does this make a polynomial number of mistakes in the dimensionality? This has nothing to do with dimensionality. It depends on we have to now think about whether this is a mistake bound algorithm by looking at what C is. The next question is, can we do better than this? Can we do better than this algorithm? The answer is yes. And that gives us the halving algorithm. But before that, let me just to see if make sure that everyone's on the same page. I'm going to launch a poll. You should be able to see this now. Suppose you have a concept class C that has 256 different functions. Pick the statement that that is most true. And while you're doing that, also feel free to ask questions. And I've realized that I can make polls anonymous on this. So all polls are anonymous, so don't feel shy about voting. While that's happening, there's a question: C is finite. Yes, C is finite. For the purposes of this discussion, C is finite, which is why we are able to talk about the size of C. I think about 3/4 of you have answered the poll, and so I'm going to end it right now because in the interest of time, and I'll just show you the results. So a majority of you are saying that the con can make at most 255 mistakes, and that's the right answer. The reason for that is the size of C in this example is 256. The number of mistakes that can be made is at most the number of concepts there are minus 1. So it cannot make 300 mistakes because there are only 256 functions. It cannot possibly make more than those many mistakes. It can make at most 255 mistakes because we have that's the size of C minus 1. Those of you who picked the other two options, I hope this clarifies things. If not, we can talk more. There's a clarification question. C does not tell us anything about the number of examples we are given. No, we're not. But it does tell us that the number of examples we are given one example per round. And what this I have informally proved, you can make this a formal statement if you want. I have proved that the number of rounds can at most be, the number of mistakes can at most be size of C minus 1. We may be given way more number of mistakes, way more number of examples, but the number of mistakes is only size of C minus 1. The number of examples shown might be infinite. We may have to wait forever to make these mistakes, but we can't make more than these many mistakes. That's what it is. So now let's talk about the halving algorithm. The goal of halving is also the same thing. We are given a concept class C, and our goal is to learn a certain function that the teacher chose. We'll proceed. Halving proceeds essentially in the same way as con. We will initialize C0 to be the set of all possible functions, and we will keep constructing a series of sets of functions like before, Ci at each round. That keeps reducing over time. And in the end, we will declare learning to be successful when we have found just one function inside the set, when we have come to a set with exactly one function, which has to be the right function. It's a slightly more involved definition than what we saw before. When an example shows up, we have to define what prediction is, and we have to define what update is. Prediction with halving proceeds as follows. When an example shows up, what we will do is ask every function inside the set Ci to make a prediction. Let's call these functions hypo h. And if a majority of them say the prediction is true, then we'll say that the prediction is true. If the majority of them say a prediction is false, then we say the prediction is false. Essentially, we ask the majority of the functions in CI, in the current set of hypotheses we are entertaining, to make a decision. So that's what's written here. If the number of functions that says 1 is more than the number of functions that says 0, then we say the function is then we predict 1. Of course, it implies that all functions in F is we are only dealing with Boolean functions right now, so we are assuming that the functions return 0 or 1. Now the next question is how do we make an update? Remember, this is a mistake-driven algorithm, so updates happen only when there's an error. With the prediction, which was decided using the scheme here, if the prediction is not equal to the ground truth is f of x, then what you do is we remove all functions, all elements of CI that disagreed. We remove all elements that disagreed with f only, and only keep those things that agree with f. So you update CI plus 1 to be only those functions that agree with f on this example. Okay, so prediction is done by asking every function to vote on the label and picking the majority vote, and updates happen by only if there's a mistake, and if there's a mistake, we remove everything that disagrees with the ground truth from the set. So let's see how many mistakes Halving will make. This is going to be interesting. So let's say that Halving makes n mistakes, some number of mistakes. Here n is not the number of dimensionality. I should use some other letter here, but for the purpose of this slide, let's say n is the number of mistakes. So how does Halving proceed? It starts off with C0, and then it goes to C1. When there's a mistake, it goes to C2, and so on, and then it goes to Cn. So that's why Halving has made, and let's say Halving makes n mistakes, which means after n mistakes, there's exactly one element in the last set, which means the size of Cn equals 1. Now, let's think about what happened between Cn minus 1 and Cn. How did we make a prediction? We looked at some example came in, and we asked all the functions to make a prediction and took the majority label. There was a error that happened, and that's why we had to make an update. What does it mean when a mistake happened? When the mistake happened, remember that we only keep those elements that agree with f, which means we remove all elements in Cn plus 1 that disagree, that were wrong. But what does it mean that it was wrong? We made so let's say we have Cn plus 1, so Cn minus 1 consisted of some functions, f0, f1, f2, and many functions of this kind. And let's say all of these functions predicted some label, let's say true, and this thing predicted false. And it turns out this was a mistake. That means a majority of the functions in Cn minus 1 predicted the wrong label. That is why there was a mistake. And we're going to remove all of them. So we're going to remove all of these, and we are left with exactly one thing inside Cn, which means the size of Cn should be less than half the size of Cn minus 1, because otherwise, that's why the majority decision was wrong. The majority decision was wrong, and we got rid of this the incorrect functions. So the size of Cn was less than half the size of Cn minus 1. But we can keep making the same argument again and again. The size of Cn minus 1. How did Cn minus 1 come into existence? It came into existence when more than half of its predecessor were wrong, and as a result, more than half the functions got removed. So the size of Cn minus 1 is less than half the size of Cn minus 2, and so on. At every step, we keep halving. There is a question about what happens when there is exactly half of them predict a majority. I'm not going to worry about that. Let's say we toss a coin, or you just pick one of these things. So every time a mistake happens, the hypothesis space that we are entertaining gets reduced by half. So with one mistake, it got reduced by half. With two mistakes, it got reduced by half square, and so on. With n mistakes, it gets reduced to half 2 power, 1 over 2 power n times the number of concepts in the original class. So the number of mistakes is going to be less than 1 over 2 power n times the size of C. But let's now see, we know that learning stopped when exactly one function remains. We can compare these two things. And so you have 1 less than equal to, not less than equal to, but strictly less than 1 over 2 power n size of C, which means the size of C is less than 2 power n, but n is the number of mistakes. So n is less than log to the base 2 of size of C. The number of mistakes is less than log to the base 2 of size of the number of functions there are in the original class. So it's always log to the base 2. So the halving algorithm cannot possibly make more than log size of the concept class number of mistakes. Are there any questions? And while you're thinking of questions, let me launch a new poll. Let's say we had the same concept class that were in your original poll. How many mistakes will halving make on it? Or what can you say about halving? Halving, remember, can make no more than log the size of C number of mistakes. It does matter that it is log 2 because we are actually seeing that there's a log here, but I mean, it's just a technical detail. It's not going to make a big difference. What's the constant between friends? So many of you, almost all of you, are agreeing that halving will make 8, no more than 8 mistakes. And why is it 8? Because 8 is log of 256. So halving will make no more than 8 mistakes on C, whereas Con would have made no more than 255 mistakes on C. So halving is not going to make more mistakes than Con. So it's halving that makes at most 255 mistakes on C. This is just a proof of concept algorithm. I want you to keep in mind that this is not easy to compute. But despite that, in some concept classes, halving is optimal. For all Boolean functions, halving is optimal, and optimal has a very specific definition. For the most difficult concept in the class, for the most difficult sequence of examples, an optimal algorithm will make the fewest number of mistakes. For some certain classes of functions, halving is optimal, but not in general. And in some cases, there are functions that are there are algorithms that can make fewer mistakes for functions that are not Boolean. In general, to be optimal, we need to do a lot more. We need to worry about the expected number of mistakes, which can be even harder to compute. I'm not going to spend any time talking about this. And we have only 2 minutes left. So let me quickly wrap up halving and pause for questions after that. Halving is a simple algorithm for finite concept classes. What it does is it stores all hypotheses, the set of all hypotheses that it keeps iteratively refining. At each step, it receives an input, and the prediction is the label of the majority of hypotheses that are still under consideration at that step. And if this prediction is wrong, it removes all inconsistent examples. In other words, if the prediction of the majority of the hypotheses is wrong, it removes the majority function subset. It makes at most log size of C number of mistakes, and we just proved that. You should be able to, I want you to work through that proof offline, and if there are questions, come back or ask me in office hours. There is a technical detail. It's not always optimal because we care about minimizing the number of mistakes in the future. And there's another thing, in the presence of noise, this whole thing gets destroyed because once a function is eliminated, it gets thrown out forever. It's not going to come back. But if there is noise and it accidentally eliminated a function, we'll be in trouble. So maybe instead of eliminating functions, we might want to downweight them or upweight functions that are good. And this line of thinking takes us to this notion of multiplicative or additive updates, where we multiplicatively or additively upweight points functions. There's one question, I'll take that and then stop. In addition to a finite concept class, this is only for Boolean functions. Um, it's for functions where the range is Boolean. The domain need not, but for the purposes of this discussion, let's pretend that it is, because we can make any finite concept class into a, if the range is Boolean, into a Boolean function. All right, I'm going to pause now because we are at 10:30 and I would hate to keep you waiting for longer, but please do go over this offline. And this is the kind of stuff that where we talk about sizes of hypothesis spaces and talk about difficulty of learning as a property of that. That we'll be looking at a lot more, and this is the kind of stuff that really forms the theory of machine learning. So we will be touching on these kinds of theoretical ideas every now and then. So please do go over this and come back with questions. I'll stop now, and I have office hours. So I'll start that in another 15 minutes. If you have any questions, you can come and chat with me there also. All right, I will see you next week if you don't come to office hours, or rather, I'll see you on Thursday. Thanks.